Oxidation Reduction, Lecture 2. Remember, there are 3 essential steps in balancing equations by the half-cell method. They are dividing the reaction into oxidation and reduction half-cells, and then balance each of those half-cells independently, but make them equal. In other words, make electrons lost equal electrons gained. And then add those half-cells algebraically. All right, we're going to apply that to a couple of equations. This is a good oxidation reduction reaction for us to try. Now, if you'd like to try it on your own, go right ahead, stop the recording, and then come back to it, and I'll show you how I worked it. But this is what I would do. Go through first and make sure you know the oxidation state of everything. Of course, the iron is noted on both sides, and the chromium is noted over here. But on the left, oxygen is a -2. There are 7 of them, gives you a total of -14. And what does chromium have to be to go with the -14 to equal the -2? And the answer is, it has to be a total of +12. So each chromium is a +6. All right, I think now we know the oxidation state of everything, so let's go through and balance this. I'm going to start with iron. Doesn't matter which one you start with, whichever you choose. The Fe+2 is going to go to the Fe+3. And as it goes from a +2 to a +3, it's going to lose an electron. And we lose electrons on the right. In other words, the Fe+2 converts to an Fe+3 plus an electron. All right, is that one balanced? Well, we have a 2+ over here, we have a 3+ and a -1, so that's a 2+ over here. So the answer is yes, that part is balanced. So let me get rid of this now. All right, back to our problem. Let's go to chromium. Chromium occurs in the dichromate in this problem. And it's going from dichromate to the chromic ion. Now, folks, this is really important also. See that 2 right there? You've got 2 chromiums on this side. You've got to have 2 chromiums over here. Each chromium is going from a +6 right here over to a +3. And as it goes from a +6 to a +3, each chromium is gaining 3 electrons, but there are 2 of them. So it is gaining 6 electrons total. Got that? Good. Now what about oxygen? Oh my goodness. Here's oxygen. There are 7 oxygens here. So we're going to have 7 waters over here on this side. Okay, now let's check our charges. Our charges over here tell us that we have -8 on the left, and we have +6 on the right. So how do we get these charges to balance? This is where our acid comes in. And it tells us that we're going to be adding hydrogen ions, which is adding positive charges. If we add positive charges to the right, that only makes this +6 grow to be +7, +8, or whatever, and it makes bad matters worse. What we have to do is add positive charges to the left. So how many positive charges are we going to add on the left to go with a -8 to equal +6? And the answer is 14. And what is our source of these positive charges? It's the hydrogen ion. So we put 14 hydrogen ions on the left. Okay, now let's check our charges. Let me get rid of some of the stuff down here and go through and check our charges again. Make sure we are absolutely right on everything. Make sure that we've got everything balanced. Okay, we have +14, and we have -6, and we have -2, and on this side over here we have +6, and water of course is 0. Oh, our charges check out very nicely. Good. Now we come to another crucial point. How do we make electrons lost equal to electrons gained? Well, we have 1 electron out, and we have 6 electrons in. So we multiply this half cell by 6. And that makes electrons gained and lost equal. Now we're ready to look at our total equation. We have 14 hydrogen ions plus 6 Fe plus 2s. And the order in which you write these really doesn't matter. And we have a dichromate, and that is going to produce 2 chromic ions and 6 iron ions and 7 waters. Now there's something I neglected to mention. Did you notice that the hydrogens balanced out just fine? That's right. So here is your total ionic equation. Here is a particularly interesting oxidation reduction reaction that has several features that can really help you in balancing equations later. First of all, note that it occurs in a neutral solution, neither acid nor base. Let's go through first and assign oxidation states as the way we normally do. Bromine is a 0. Carbon here, go figure, it's a 4+, and oxygen, of course, is a 2-. You know how to do that, don't you? Bromine here is marked, it's a -1. Bromine here, let's see, oxygen is a -2, and there 3 gives you a total of -6. To equal the -1 charge, then, this bromine must be a +5, and there's only one of them, so it is a +5. Oxygen here is a -2. There are 2 giving us -4. Carbon must then be a +4. There's only one, so it is a +4. Okay, good. Now we've got these things marked. Let's see what's changing. Well, let's see. Bromine right here is changing to the bromide ion. Okay, that looks good. Look, carbon is not changing anywhere. What is changing? Well, bromine is also changing to here. And since it is changing both ways, this kind of a reaction is called a disproportionation. That is D-I-S proportionation. P-R-O-P-O-R-T-I-O-N. Disproportionation reaction. Sometimes that's called an auto-oxidation reduction reaction. Okay, auto-oxidation reduction. Well, let's see how to manage these, because not only is it a disproportionation reaction, it occurs in a neutral solution. Well, let's go back and get rid of a lot of these scribbles here. I trust you have that down. And proceed with balancing our equation. Now we're going to start with bromine. The question you may have is, how to handle bromine? I would take bromine just like this. After all, you have so many bromine molecules in this thing. So take one of them and say that bromine is changing this way. That Br2 is going to a Br-. I have 2 bromines on the left, so I'm going to have 2 bromines on the right. Each bromine then is gaining 1 electron, and there are 2 of them, so I'm gaining a total of 2 electrons. Get the idea? Good. Now let's go to the other one. Let's take some of the one of the other bromine molecules and say this, say this Br2 is producing BrO3 with a -1. Now each of these bromines is going from 0 to +5. Oh, but I have 2 of them here, so I have to have a 2 here. Don't forget to put that 2 in there. Each bromine is going from a 0 to a +5. Each bromine then is losing 5 electrons, but you have 2 bromines, so you are doing what? You are losing 10 electrons. Got the idea? 10 electrons. All right, now let's balance the charges. The charges on this one balanced fine, but the charges here are really off because this is 0, and over here this is a total of -12. And the problem is we're in a neutral solution, so we can't use hydrogen ions or hydroxide ions. We have to use an ion that's not undergoing a change. Well, look at carbon dioxide. In this, carbon is a +4 and oxygen's a -2. And it is changing to carbon dioxide over here. The carbonate is changing to carbon dioxide, but the oxidation states haven't changed. So we can use the carbonate to balance our charges. Carbonate is a -2, and I need 12 on the left, 12 negative charges, so I'm going to use 6 carbonates on the left. Now let's see, our charges are balanced just fine. Now that our charges are balanced, let's look. Is everything else balanced? Well, of course not. I just added carbon. I have 6 carbons on the left, so I'm going to have 6 carbons on the right. Therefore, I've got to have 6 carbons on the right as carbon dioxide from right here. So that's 6 CO2. Now let's check our charges and oxygen and everything. Well, let's see. 6 times 2 is -12 here. And this is -2 here and -10 here. Oh, that's looking good. So our charges are all balanced. But we had already checked that. We're just double checking. What about carbon? I've got 6 carbons on the left. And I have 6 carbons on the right. That looks good. All righty. What about oxygen? I have 12 oxygens over here on the right. Oops, wait a minute. Right here I've got 6 more, so I've got 18. Let's see, 12, 6, 18, yes. And over here on the left, I have 18 oxygens over here also. So everything is looking good. Both half cells are balanced. We've got the electrons lost and gained noted. So let's take these 2 half cells and add them and see what we have to do to get the electrons completely balanced, and then we'll add them up. Well, I have 10 electrons out and 2 electrons in, so I have to go in here and multiply this top equation by 5. All right, that makes the electrons in and out right. Let's add them up. So that's 5 Br2s plus 6 carbonates plus a Br2 is going to produce 2 bromide ions. Oh, no. That's not 2 bromide ions. I forgot to multiply it. It's going to produce 5 times 2 is 10 bromide ions plus 2 bromates plus 6 carbon dioxides. All right, let's go through and do it algebraically. 5 bromines here and 1 bromine here is going to make 6 bromines. and 6 carbon dioxides. I mean 6 carbonates. Listen to what I mean, not what I say. And that is going to produce 10 bromides and 2 bromates and 6 carbon dioxides. Now, do you notice that this equation has all multiples of 2 as the numerical coefficients? So let's go through and reduce the equation. This becomes 3 Br2s and 3 carbonates, giving us 5 bromides and 1 bromate and 3 carbon dioxides. Okay. Now I can imagine that you're saying, why didn't I start out with my Br and break it up into 2 individual bromine atoms to keep me from having to reduce it at the end? Well, there are a couple of good reasons for this. One, if in the long run you'd come out with an odd total number of the bromines, you'd have been in trouble, because then you would have had to invoke fractions. And the other thing is, sometimes you don't have to wind up reducing it. Sometimes it comes out right just as it is. So anyway, there's the trick to that. Balancing by oxidation number. Now in this case, the equation is balanced without dividing it up into oxidation and reduction half cells. Instead, what we do is use the oxidation state changes to determine whatever the numerical coefficients are going to be. Well, let's look at one. Here we have copper and nitric acid giving cupric nitrate, nitric oxide, and water. Start out by assigning oxidation numbers. Now I'm going to pause a second and let you go through and assign oxidation numbers to everything. When you get through and are ready to go on, you should pause the video for this, and then when you get through and are ready to go on, click the video and let me show you what I came up with. I came up with these for my oxidation numbers. Do you agree? All right, the next thing we do is note the electrons gained and lost. Well, copper is losing 2 electrons right here. What else is changing? Nitrogen is changing in one place and not in the other, so you have to be careful now with this. Nitrogen, as it goes from nitric acid to NO, gains 3 electrons. Now let's make electrons gained equal electrons lost. Well, we've got 2 electrons lost and 3 electrons gained. Oops, we're back to the 3-2 scenario, aren't we? Multiply this one up here by 3, which means you need to put a 3 in front of copper here and a 3 in front of copper here. Now, what about the other one, the gaining 3 electrons? We multiply it by 2, which means we put a 2 here and we put a 2 over here, because those are the ones that are bracketed. You don't mess with the others. Now correct your nitrogen. Well, you have 2 nitrogens that are changing, but oh look, you have 6 nitrogens that aren't in the cupric nitrate. They're not changing. So those extra nitrates were spectators, but you've got to account for them. So how many nitrogens do you have total? You've got 2 on the left, and you've got 6, and 2 is 8 on the right. So let's change the 2 on the left in front of nitric acid to 8. Yeah, changed it to 8. Correct oxygen. Oh my goodness, let's see. I have 24 oxygens on the left. I have 3 times 2 is 6 times 3 is 18, 19, 20, 21 on the right. So I need 4 here, because to get it to 24, I need 3 more than what I had, and I had 1, so I need a total of 4. Check hydrogen. 8 on the left, 8 on the right, 3 coppers, 3 coppers, 8 nitrogens, 8 nitrogens, 24 oxygens, 24 oxygens. Hey, it's balanced. Now, you might want to stop the video. I may have gone too fast for you here, and go through and finish up your notes and try your hand at that and be sure you have it. Now, I want you to pay attention to one thing, though. You really need a complete equation to do it this way. With a half-cell method, you can complete in balance. But with this, you need a completed equation if at all possible. Otherwise, do it by the half-cell method. Here's a good one. Zinc plus nitrate and a base with water gives you ammonia and a complex. Okay, this is going to be a really, really interesting reaction. I see right now that I need to show you some tips and tricks on this one. So bear with me. First thing, let's assign those oxidation numbers. So pause the video, assign your oxidation numbers, then come back and check and see if we agree. Well, this is what I have. Now watch out for that nitrogen, going from a +5 on the left to a -3 on the right. Be careful with that. Okay, we've assigned the oxidation numbers. Now, let's note the electrons gained and lost and make them equal. Well, what's changing? Zinc is going from a 0 to a +2, and in the process is losing 2 electrons. What else is changing? That nitrogen is going from a +5 to a -3, so it has gained 8 electrons. Now, to make electrons lost equal electrons gained, we need to multiply the top by 4, which means 4 zincs here and 4 zincs here. Okay. Now, technically, we multiply the bottom one by 1, but we don't actually put anything in front of those because a 1 is already understood to be there. Okay. Double check the nitrogen and zinc and be sure they're balanced. 4 zincs and 4 zincs and 1 nitrogen and 1 nitrogen. Yep, they look good. All right. Now let's balance oxygen. And this can get a little stinky, because on the left you have 3, 4, 5 oxygens, and on the right you have 16 oxygens. Well, you start juggling things, and you don't want to mess with the nitrate because the nitrogen's balanced. So you got to juggle the hydroxide and the water, and it can get a little hairy. So, but look at this. Charges must be equal on both sides. Well, we've got a -1 here and a -1 here. That gives us -2 over here. We've got a -8 on that right-hand side. So we got to have -8 on the left, but we don't want to mess with nitrate. So we need the nitrate to be a -1 and the hydroxide to give us a total of 7. Yeah. So put 7 in front of your hydroxide. Look what you just did. You got 3 oxygens from the nitrate, 7 oxygens from the hydroxide, that's 10. 1 from over there. Oh, we got to balance the hydrogens. Yeah, let's see. 6 hydrogens here. Because we've got over on the right, we've got 4 4s are 16, 3s 19. We've got 7. Yep, got to have those 6 waters there. So how about it? Are we balanced? There are times in working problems in chemistry that you go through and balance an oxidation reduction reaction, and you balance it and come out with a net ionic equation, only to get over to the problem and find that, oh my goodness, your problem might require you to know the quantity of some of the spectator ions. And to get that, then, you're going to have to figure out what the molecular, or you could, by the same token, the total ionic equation would be. But let's go to the molecular equation, because there are times you need to figure that one. Now, look at what you have. Look, for example, at the 7 hydroxides here. What would you use for the hydroxide? Well, how about sodium hydroxide? And you know that sodium is going to become a spectator ion, but that's fine. It's a good spectator ion. Well, what about the nitrate? What would you use here? How about sodium nitrate? Try to keep this thing as simple as you can. Well, what am I going to use down here? Well, I've got some sodiums that are going to be stray, so I could put some sodiums with this, and since this is a -2 charge, I could form some Na2ZnOH taken 4 times. Yeah, I could form that. That ought to do it. All right, let's rewrite this equation now. I've got 4 zincs plus sodium nitrate plus 7 sodium hydroxides plus 6 waters, producing ammonia, which is probably going to come off as a gas, plus the 4ZN, no. Got to put the sodium in there. 4Na2ZnOH taken 4 times. Now let's see if we're balanced. I've got 4 zincs here, 4 zincs here. I have 1 and 7 is 8 sodiums, 8 sodiums. I have a nitrogen here and a nitrogen here. I have 3 oxygens here, and 7 here is 10, and 6 here is 16 oxygens. And I have 4 times 4 is 16 oxygens. Let's look at hydrogen. I have 7 hydrogens here, and 12 here is 19 hydrogens. I've got 4 times 4 is 16, and 3 is 19 hydrogens here. So my equation is balanced, and my ratios of the critical things that produce the net ionic equation have not changed. Now, sometimes when you do this, you're going to generate some additional spectator ions, but you'll see that when you run into it. But get a handle on how you might handle conversion from net ionic to molecular equations. When we talk about stoichiometry, we're talking about calculations from oxidation reduction reactions, and 2 steps are involved, but it's really nothing new. You have to complete and balance the oxidation reduction reaction, and then perform the calculations based on that. But just to give you a good review and to show you an example, let's do one. In this problem, we're asked to calculate the volume of this solution right here, needed to react with this solution right here. And we're told that carbon dioxide and the manganese ion are produced. So we're going to have to write and then balance the oxidation reduction reaction and then work the problem. So it's in 2 parts. Now I'm going to start out with writing the equations and getting them balanced first. And I'm going to do it as net ionic because, quite frankly, that's the easiest way to do it. Now if you want to, stop the video and try your hand at writing and balancing this equation, and then come back and check, make sure I did it right. But I'm going to start with the carbon dioxide and say the carbon dioxide was formed from the C2O4 going to CO2. There are 2 carbons there, so I've got to have 2 carbons here. The carbon is going from a +3 here to a +4 here. So each carbon is losing an electron, and there are 2 of them. So I'm losing 2 electrons. Now let's see. The carbons are balanced, the oxygens are balanced, and the charge is balanced. Good. Let's go to the other one. In this other one, I have permanganate. That's got to be the source of the manganese ion. And it is going to the manganese ion. In the process, manganese is going from a +7 in permanganate to a +2. So it must be gaining 5 electrons. Goes from 5 electrons over to the manganese ion. But what about the oxygen? So I'm going to have 4 water molecules to balance the oxygen. Okay, now let's see about the charges. My charges here are -6. My charges here are +2. I'm using an acid solution right here. So I'm going to have hydrogen ions, so I'm going to need 8 hydrogen ions to balance this equation. Yeah. All right, so the 2 half cells are balanced independently now. Let's see what the electrons lost and gained are going to do to us. We have 2 electrons lost, 5 electrons gained. We need to multiply this top half reaction by 5 and this bottom half reaction by 2. Now, having done that, let's write this then as a balanced, complete, net ionic equation. And we have 16 hydrogen ions and 5 binoxylates and 2 permanganates and that is going to produce 5 times 2 is 10 carbon dioxides and 2 manganese ions and 8 water molecules. But now I need to convert this to a molecular equation. So, to convert it to a molecular equation, what acid shall we use? Well, I suggest hydrochloric. So how about 16 HCl plus, and how about, well, we've already been told, it's sodium oxalate, right? So it's 5 Na2C2O4, okay, plus, and the permanganate is potassium permanganate, and that's 2 potassium permanganates. And that is reacting to produce 10 carbon dioxides. Now, what's that manganese ion going to go with? Well, it was sitting out there as a +2, and we've got to write this molecularly. How about picking up some of the chlorine the chloride ions that are going to be running around loose in here? So let's put it as 2 MnCl2s, and let's see, plus 8 waters. All right, let's see how we're looking. Well, let's see. We have 16 hydrogens. We've got 16 hydrogens. We have 16 hydrogens over here and 16 hydrogens over here. Oh, that looks good. I've got 5 times 4 is 20 oxygens here, and 8 makes 28 oxygens here. I've got 10 times 2 is 20 oxygens here, and 8, 28 oxygens. So the oxygens are all balanced. That's looking really good. Okay, sodium. I've got
10 sodium ions over here. I don't have any over here. What am I going to do about my sodiums? Well, how about some sodium chloride? How much sodium chloride do we need? Well, I guess we need 10 of them. About 10 sodium chlorides. Okay, so now sodium is balanced. We've got 10 carbons and 10 carbons. Oxygen's already balanced. And we have 2 potassiums over here. 2 potassiums? Where's the potassium going to go? Well, it's got to go with chloride, I guess. So how about 2 potassium chlorides? Now let's see if our chloride is right. We've got 16 chloride ions over here on the left. We have 4 here, 2 here, that makes 6, and 10 here makes 16. Guess what? It's balanced. Now, we're ready to work the rest of the problem. Let's take our 25 milliliters of our potassium permanganate times 0.0233 moles per liter times the stoichiometric ratio, which is 5/2, to get us over to the sodium oxalate, times liters over 0.0199 mole. Now let's cancel units. Moles and moles cancel, liters and liters cancel, and we should come out in milliliters. And I get for an answer to this 73.18 milliliters. It's a really good problem.
Oxidizing and reducing agents. Folks, how can you predict when something is going to be an oxidizing agent or a reducing agent? Well, there are several factors that are involved here. But let's start out by reviewing the range of oxidation states for the representative elements. That'll be a good starting point. Get a periodic table. Look at it. Now, for the 1A elements, what are the common oxidation states or the common range of states for them? 0 or +1. Granted, hydrogen can be a -1, but for the rest of the 1As, it's 0 or +1. What about the 2As? What are the oxidation states for that? Well, they are generally 0 or +2. The 3As, what are those? The 3As run from +3 to -5. Now, we went through all of that earlier in this course, so remember it. But this is a time to review, so it can be anywhere from +3 to -5. +3, +2, +1, 0. -1, -2, -3, -4, and -5. What about the 4As? Well, the 4As, that carbon family, run anything from +4 to -4. +4, +3, +2, +1, 0, -1, -2, -3, -4. You've got it. The 5As, from +5 to -3. From +5 through 0 to -3. The 6As, from +6 through 0 to -2. The 7As, from +7 through 0 to -1. There are some things you need to keep in mind when you're trying to decide whether or not a particular compound or an element could be an oxidizing agent or a reducing agent, or either. Remember, oxidizing agents gain electrons. Therefore, the only things that can act as oxidizing agents are those things that are capable of gaining electrons. Another thing is reducing agents lose electrons. So the only thing that can act as reducing agents are those things that are capable of losing electrons. Consider iron, for example. Now, the common oxidation states of iron are Fe at 0 when it's an element, Fe with a +2 charge, and Fe with a +3 charge. Are there other states that are very much less frequently occurring? Very possibly, but we're only looking at the common states. Can Fe with a 0 charge act as a reducing agent? In other words, can elemental iron act as a reducing agent? Now think about it. And the answer is certainly it can. Why? Because Fe can lose electrons to form either the ferrous ion or the ferric ion. Okay. Well, can Fe0 act as an oxidizing agent? And the answer is not likely. Why not? Do you know of a case in which iron, as the element, gains electrons? Well, consider the ferric ion and ask yourself, can the ferric ion act as a reducing agent? Can the ferric ion act as a reducing agent? Can the ferric ion lose some more electrons? The answer is no. Why not? Well, it's already lost all the electrons normally possible, and we're not going to those extreme states. We're only dealing with what is normally possible. Well, can the ferric ion act as an oxidizing agent? And the answer is, can it gain electrons? Certainly. It can form the ferrous ion or metallic ion, either one. Now consider the ferrous ion, the Fe+2, and ask yourself, can the ferrous ion act as a reducing agent? Can the ferrous ion lose electrons? The answer is yes, it can. How? Because it can lose an electron to form the ferric ion. Okay. Well, can the ferrous ion act as an oxidizing agent? Can it gain electrons? And the answer is certainly. It can form iron with a 0 charge. Are you beginning to get the idea? Well, we need to look at this in a little bit more extensive way, but this is the beginnings of your process. To summarize this before we go on, if an element or an ion is at one extreme of its oxidation state range, it can only change in one direction. If the range for iron was, for example, only that it could be 0, +2, and +3, and if it was a 0, the only thing it could do would be to lose electrons. Well, you get the idea. If an element or an ion is somewhere in the middle of the oxidation state range, then it can go in either direction. A few pointers. The pointers come with the polyatomic ions. If you're looking at a polyatomic ion, such as permanganate, don't consider oxygen, just consider the manganese. In this case, the manganese, which is a +7 charge. The only time you consider oxygen is when it is present as a peroxide or as O2. When it's present as a peroxide or O2, it's very rare that you're going to find oxygen changing from a -2 to one of the lesser states. It's not to say that it's not possible. It's just not one of the really likely ones. Stay within the common oxidation state range unless you're given some other information. So those ranges that we've talked about, stick in there. We're getting ready to apply all of this by building a table that looks like this. We're going to go through and using the information and the ideas that we've been talking about, we're going to fill out this table. So you need to go back and review everything, make sure your notes are clear. And in the next lecture, we will start off by building and completing this table. A better way to teach and learn chemistry.